In the last video, we looked at the first example of a hypothesis test involving a population mean, and this example involved an urgent care, and at this urgent care, the staff wanted to reduce the wait time for patients, and so the staff implemented a new check-in system. And after they implemented this new check-in system, they conducted a study to see if that new check-in system was successful in reducing the wait times for patients. So in the last video, we summarized the information in the description. We stated the hypotheses. The null hypothesis was that the population mean wait time for patients with the new check-in system was just the same as the mean wait time for patients with the old check-in system. And then the alternative hypothesis was the population mean wait time for patients in the new check-in system is now lower than the mean wait time that patients had under the old check-in system. Also in the last video, we went over step 2, which was to verify the requirements for doing this hypothesis test. And in this video, we'll go right on to step 3. Step 3 is to test the hypothesis using a t-test. That's just what this particular test is called. There are 2 or sometimes 3 approaches to testing any hypothesis, but remember that you won't need to know all 2 or 3 approaches to testing hypotheses. On a quiz or test or the homework, you can use any one approach that you prefer. So one approach is the classical approach, or the test statistic approach. And the first thing that is helpful to do in this approach is to sketch the t-distribution probability curve, and then use table 7 to determine the cutoff value, which is a t-value, for the region of the curve that will represent unusual or significant study outcomes. We'll make a note that this is a left-tail test because our alternative hypothesis was less than. And in the last video, I didn't really emphasize why this is less than and why this is a left-tail test. Remember that in the description of the hypothesis and the study, the staff implemented this new check-in system because they wanted to reduce the wait time for patients. And in particular, they wanted to know, is this new check-in system effective in reducing the mean wait time? So that word reduce, it is similar to decrease, and decreasing implies less than. So the alternative hypothesis is less than. This is a left-tail test. Also note that alpha is 0.10, and this is the area under the left tail of the curve. Here's a sketch of the t-distribution. The mean is 0. T right here is the cutoff value for the left tail, and the area of that left tail is 0.10. So we'll go to table 7, the t-distribution table, and look for the critical value for t for a left tail test and for when alpha is 0.10. To use table 7, you'll need 2 pieces of information. You need the degrees of freedom, and you need the area under the tail of the curve. The degrees of freedom is n minus 1, so 36 minus 1, that's 35. The area under the tail is 0.10, that's the alpha. Now we'll go to table 7 and look up the value of the critical t-value. And so here's 35 degrees of freedom. Here is the area of the tail, which is 0.10, and they line up at 1.306. So according to table 7, our critical value is 1.306, but this is not quite the correct value. Table 7 gives you the t cutoff values for the right tail of a distribution curve. So what we just found out from the table is that on the right side of the curve, if alpha was 0.10 for the right tail, the cutoff would be 1.306. But that's okay. The t-curve is symmetrical. We want to know the cutoff for the left tail, and it's going to be the same value except just negative. So our actual cutoff t value is negative 1.306. The next thing is to calculate the test statistic. The test statistic is a t-value. Here's the formula for the test statistic. Remember that the test statistic, in general, the meaning of it is that it's showing you how far above or below your study's outcome is from the mean. And in that effect, it's measuring the significance or the unusualness of your study's outcome. Note that in the formula, this mu sub 0 means the population mean of the null hypothesis. So the null hypothesis was 24.8 minutes, so that will be for the mu sub 0. Also, our sample size was 36, the sample mean was 23.6 minutes, and the sample standard deviation was 3.5 minutes. Put all those values into the formula, and the t-test statistic comes out to negative 2.0571. The last thing that we'll want to do is determine whether this test statistic is inside the critical tail of the curve, in other words, to the left of the cutoff value, or outside the critical tail. And remember that if the test statistic is inside the critical tail, then that means that the results of the study are unusual and significant, and you would reject the null hypothesis. And you would conclude that the study's evidence is supporting the alternative hypothesis. If the test statistic is outside the critical tail of the curve, then the study's results are not unusual and not significant, and you would not reject the null hypothesis. And in effect, that would mean that your study's evidence is not supporting the alternative hypothesis. So here is the curve. Our test statistic was negative 2.0571, and that is inside the tail. That's somewhere way inside here. Negative 2.0571. So it is inside that critical tail. That means that the results of our study are unusual and significant, and for that reason we can reject the null hypothesis. Here's another approach to testing this hypothesis, the p-value approach. So remember that a p-value is a probability, and in particular it's the probability of getting the result of a study or something more extreme, assuming that the null hypothesis is true. So to calculate that p-value, you can do that on a Casio graphing calculator or on the TI-83 or 84 calculator. In these notes are the steps for what you would do on each kind of calculator. You take these steps. Ultimately, you want to get to this function on the Casio called 1s. And then when you get there, you want to make sure to put in the correct inequality for the alternative hypothesis, put in the value for the null hypothesis, your sample mean, sample standard deviation, and sample size. On the TI-83 and 84, ultimately you'll take these steps and you want to get to the function called t-test, and you'll put in the null hypothesis value, the sample mean, sample standard deviation, sample size, and also you want to make sure to put in the inequality that's matching the alternative hypothesis. So either way, when you calculate it, you'll get a p-value of 0.0236. And the last thing that you want to do is to compare that p-value to the alpha. Just as a reminder, the meaning of this p-value is that it's the probability that a random sample of 36 patients would result in a sample mean of 23.6 minutes or less, and a sample standard deviation of 3.5 minutes, assuming that the null hypothesis is true. In other words, assuming that the mean wait time under the new check-in system is still just about 24.8 minutes. So remember that when you compare your p-value to alpha, if the p-value is less than alpha, that means that your study's results are unusual and significant, and you would say that you reject the null hypothesis and conclude that your study's evidence supports the alternative. If your p-value is greater than alpha, then that indicates that your study's results are not unusual and not significant, and you would say then that you do not reject the null hypothesis. And that means that the evidence from your study is not sufficiently supporting the alternative. For this study, we had a pretty small p-value. It was less than alpha, and that means that for this study, our results are unusual and significant, and we will reject the null hypothesis. The last step, step 4, is to state the conclusion. Remember that when you state the conclusion, it helps to state it in terms of the alternative hypothesis. Our conclusion is that we reject the null hypothesis. That means that there is evidence to support the alternative. And the alternative was that the new check-in system is effective in reducing the mean wait time for patients. Alright, in the next video we'll take a look at another example of a hypothesis involving a population